Okay, thanks. So let me tell you about what we're going to cover in this talk. This is not going to be an introduction to basic OpenMP. I'm going to assume that you have some knowledge. I'm going to cover the basics in a few slides. But then what I'm really going to cover is some newer features of OpenMP, such as OpenMP tasking, OpenMP SIMD, which might be particularly useful on processors with many cores and many threads, such as KNL. I'm also going to cover Affinity. So if you are a hardcore OpenMP person that doesn't really care about tasking at all and doesn't even want to listen to it, if you go away and come back in the last 10 minutes of the talk, then I might have a couple of things that could be useful in Theta for you. So OpenMP stands for Open Multiprocessing, and it's essentially a standard for parallel execution on a shared memory infrastructure. It's been around for a very long time. It has support for all the major languages that you normally see in an HPC environment, and it provides APIs to affect the parallelization and environmental variables to allow you to control the execution in a fair level of detail and granularity. And it's supported by most of the compilers out there. So whether you're using LLVM, GCC, the Cray compiler, the Intel compiler, you will have support for this. And most of them will have support for tasking and SIMD to one level or another, depending on how mature the support for OpenMP 3, 4, and 5 is. Now, the OpenMP programming model is conceptually very simple. Most real-life programs have some serial sections, some sections that is practically impossible to parallelize. So it just has essentially a master thread that it starts, it hits a parallel region, it forks a set of a team of threads to work on that parallel region, then it synchronizes, goes back down to a serial region where only the master thread is active. Modern runtimes do not really kill the threads, they just keep them spinning for a certain amount of time to amortize the effort of spawning and killing them. So if you have multiple parallel sections and they're not very far from one another, your threads are not going to be destroyed. They're just going to be spinning and waiting for a new parallel section to spawn up. So a fairly simple setup, right? Now, the way that you control parallelization with OpenMP is through a series of directives. There is different OpenMP constructs. I like to set up OpenMP parallel construct separately from the rest because it's the one that really generates your thread teams, right? But other than that, you have a basic set of constructs that allow you to do a lot of work, and those are the parallel construct and then both work sharing, data sharing constructs, and synchronization constructs. Outside of these basic components, you also have more advanced, and maybe advanced is not the right word, it's just newer features in the language, right? So newer features such as tasking, SIMD, and a few other things, which is the part that I'm going to focus on this talk. And obviously you also have runtime functions and sort of control of the execution. Now, the way that OpenMP works is, in terms of the way that you decorate your code, is fairly straightforward, where I have two trivial examples up there on the right, one in Fortran, one in C. You see they're extremely similar. You start with a pragma OpenMP or a OMP pragma in Fortran as well. And then you have your parallel region, in this case, in the outside, and then inside we have an OpenMP for and OpenMP do, which will distribute the work on that loop across the threads that you have generated in your parallel region. And that parallel and that do, or that parallel and that for, can be combined into a single construct. Now let's move on to tasking concepts. So prior to version 3 of the standard, OpenMP was focused exclusively on data parallelism. Essentially, every thread was executing the same code, just working on different data that was blocked and assigned to the threads by the runtime based on your choices. However, that has some severe limitations. If you have work that is very irregular, it's really difficult to apply this methodology effectively without having to do some contortions in the way that you write the code, right? You might be able to do it, but it doesn't feel natural. Also, if you had, and that mostly affects dynamic scheduling, for example. Also, if you had unknown loop counts, for example, your code doesn't even have to be very irregular, but you don't know what the actual limits of the loops are, it's also difficult to get an effective parallelization out of a regular OpenMP. So in order to fix some of these challenges, task parallelism was introduced. Now, you might be asking yourself, well, what is an OpenMP task? Well, that's the definition from the standard. It's essentially something that carries the code and the data required to execute a particular thing. But you can think of tasks in two ways. You can have an explicit task, which is what we're going to describe now as how to generate it with an OMP task, pragma, for example. And you can have an implicit task, which is what happens when you have a OpenMP Parallel 4, for example. There, a thread is assigned a code and a block of data to work on, and that will be an implicit task. You didn't generate it explicitly, but it's still there, right? So that's an important distinction. I'm only going to talk about explicitly generated tasks in the rest of the talk. Now, if we have any construct in OpenMP, we need to know how to synchronize the execution. For tasks, there's two main ways of synchronization. One is for essentially independent tasks that were generated at the same level, and that would be a task wait. You can see that as an OpenMP barrier in a regular non-nested OpenMP section. You can also have a task group. And a task group is something that you would use when you have a nested environment so that you want to synchronize not only tasks at one level, but all their siblings and their descendants. So fairly simple stuff, just those two main synchronization methods, task wait and task group. Now, task decomposition, if you're wondering, well, give me an example of how this task thing works and when could it possibly be useful. So one of the ways in that this can be useful is that you often end up being able to decompose work in individual tasks, and you will have some dependencies among some group of tasks, but some others are not dependent, which makes it really difficult to just have a single homogeneous block for parallelization. I have a very silly example here with some tasks, and in these tasks we have Alice, Bob, and Cy are completely independent. They don't have any prior requirements, so they can execute anytime. Once Alice and Bob have completed execution, there is a boss task that can execute next. And once both Cy and boss have completed, the final task can be executed. You can see that there is some level of parallelism that could be lost here if we just did an OpenMP section. And we can see now in the next slide how to recover some of that parallelism. So how do we execute parallel tasks? How do we even define them or generate them? So typically what you're going to do is you're going to have your code inside an OpenMP parallel section that will generate some threads that now can execute tasks. Inside there, you're going to have a pragma OMP single in most cases, which means that a single thread is going to be taking care of the task generation. And inside that single region, you're going to have your OMP task generation. What you can see in the example is that each of these Alice, Bob, Cy, and so on tasks have been generated inside the single region. Then I close that single region so that there is essentially a synchronization point. There's another one at the end of the parallel region too. And at that point, I can execute both the boss task that depends on Alice and Bob because they both have completed. And I can, after that, since this last section of the code is executed sequentially now, I can execute the final task that depends on both Cy and boss. Now, how does this, sometimes people get a little bit confused because we're talking about threads and tasks, and how does this all work? So let me give you one example of how this can work during runtime. you hit your parallel region, and then you spawn a number of threads that are available to work on any work items that you have. Then you have one of the threads, the one that hits the single region, generating tasks for a sort of work queue that makes tasks available for execution to any threads that are free. Those tasks can be started to be executed by threads in the pool as they become free and available, right? So in this case, we have now the two threads working simultaneously on the first two tasks, and those tasks get removed from the queue. And eventually, we finish all the tasks in the queue, and we move along. At that point, we're likely to have a synchronization point and continue with our work. Now, this is all very interesting, but we have serialized half the work in that example, and that doesn't seem like a very good use of resources. So how can we fix that? Well, we can fix that by introducing a dependency clause to our OMP task generation. What this dependency is going to introduce is a concept of, hey, you cannot execute me until this input dependency has been satisfied. So if you look at the code, there is an input dependency for the last two tasks that I generate for boss and for big boss. But Alice, Bob, and Cy, Alice and Bob and Cy don't have any input dependencies. They just generate an output dependency. What that means is that now I have an output dependency from A, B, and C in this case, and I generate all these tasks for the queue, but I generate them with an annotation that says, be careful, you cannot execute boss before Alice and Bob have finished. And the runtime will take care of ordering that. And by using this dependent clause, what we do is we conserve the original parallel properties of the code that we're executing. If we didn't have this depend clause, we would have to artificially introduce task wait statements or serialize sections of the code to get the right order. In this case, I have an OMP task group there that is actually not necessary at all because since the single region is going to have an implicit synchronization point at the end, that's not needed. So you should ignore that. I don't know why I keep putting this in this slide. So we've seen one example where tasks help you preserve the natural parallelism in the code, right? There's something else that is really difficult to parallelize with regular OpenMP, which is recursive functions. And a simple example here is it's essentially a merge sort, where you keep subdividing an array, and then until you end up with a couple of items, you order them, and then you go back in the tree until you get the whole array sorted. Now with tasks, it's perfectly possible to parallelize this execution. What I do is for each one of the two calls that I have there, I define a task, and now I need to make sure that I synchronize these two before I move to the next level. Otherwise, my results are going to be incorrect. But you can see that this gives you a very powerful and very simple way of parallelizing recursive algorithms. Now, you have to be a little bit careful because with recursive algorithms, it is really easy to generate tons of tasks, many more than you actually want in terms of the hardware resources available to you. So in many of these recursive algorithm parallelizations, you're going to have a split point where you decide that you're not going to generate any more tasks once the amount of work that you have left is X, and you're going to do the rest serially. And if you do the OpenMP hands-on that I put in as part of the materials, one of the examples is going to have a simple Fibonacci generator that will illustrate this property. Some other interesting tidbits. Typically, if a thread starts executing a task and it gets interrupted for some reason, that's the only thread that can continue executing the task. So the task is tied to the thread. That's not always good. If your code is not particularly well written, it could lead to issues. So you have the option to define a task as untied, which means that any thread that is available can pick it up after it's been paused and continue the execution. It might not be the most efficient thing in the world to do in terms of performance, but for some particular examples, it might help you. Task yield is used when you want to generate your own scheduling point. I have to say I have not used task yield in my code, but I could see some examples where you're trying to do some sort of manual scheduling, but you might want to put a task yield at some point to say, I wanna stop here and I want to allow you to schedule something else for this particular thread. And then if you want to generate individual tasks out of a loop, which is something that, for example, you have a loop and you know that there's one line that is, or two lines that are always going to be tasks, right? Well, why don't just put a single annotation on the top of the loop? So you can actually do this with task loop, and that frees you from having to do it inside the loop. So it will just generate an individual task for each iteration, essentially. So that's as much time as I can dedicate to tasks, because I also want to cover SIMD. But I hope that I'm giving you an idea of how it works, how it is a little bit different from a regular OpenMP sort of fork join, completely regular execution pattern. I hope I've also given you an indication that this could be very useful if you have irregular or recursive algorithms. And I hope that you're not afraid to try it. Oh, yeah. So one of the things that I didn't cover in any detail is these tasks you can generate, and you can annotate the type of data sharing that you can do like you can with any other OpenMP clauses. But the default for a task that is generated is to have a first private for any variables that are involved, right? So just keep that in mind. Okay, so let's talk about SIMD now. And many of you are going to be wondering, why are we talking about OpenMP Cindy when my compiler already vectorizes stuff? But I hope I can explain a little bit about this. This was introduced around OpenMP standard 4. You might not care, but this might be useful to know if you want to look whether your particular compiler version supports SIMD, though you'll probably see it very quickly when it doesn't compile, but it might be useful to know. There's a bunch of things that are introduced in 4 that I'm not going to cover. So I'm not going to cover the target construct, because you don't have any targets on Theta. It's just one socket. But if you had an accelerator, you could use this pragma to say, hey, I'm not targeting the host, I'm targeting that particular accelerator. And that would be useful because it would allow you to do things like set a different vectorization length for target and the host, for example. I'm also not going to cover task groups and dependencies. That's not because you cannot use it in Theta, that's just because I don't have time to cover everything. So I'm going to cover the last two next. Well, SIMD vectorization in general is important in Theta because you have such a long vector, right? You have 512 bits. And in many cases, you're going to have assumed dependencies that the compiler is going to throw at you just for safety reasons. Now, if you can verify that either manually or with one of the available tools, as I showed with the advisor yesterday, that the assumed dependency is not there or that there's a way to fix it, then you can use OpenMP SIMD to force the compiler to vectorize. And the reason for that is that once you use OpenMP SIMD, the compiler will not look at whether there's any dependency in that loop. It will just vectorize it. So you have to be very careful, and you should always validate. Well, you should always validate your results, but particularly if you're using clauses like these that override the safety mechanisms, you should always verify that your outputs are correct and not only fast, right? OpenMP SIMD is very simple. I'm not talking about parallel OpenMP right here. I'm just talking about a single thread running along, and now we're saying OpenMP SIMD, and that's going to force vectorization of that loop. And the syntax in Fortran and in C is exactly the same. right? You have lots of clauses available to modify the SIMD statement. You have a safe length, you have a SIMD length. Essentially, safe length is how long could the vector be and still not run into a dependency, right? So that's not the vector length. That could be 500,000 because there's no dependencies in your loop. SIMD length is essentially your preferred vector length. So you would put it to 8 or 16 elements if you were doing double precision or single precision on Theta, for example. Linear and also, linear is, I was going to talk about uniform, but that's not in this slide. So linear essentially allows you to modify how a particular variable that is inside the loop has to increase in size with the loop. So if, for example, your loop had a variable that increased by 1 on every iteration, and now you have a vector length of 8, now it's going to be increasing by the vector length on every iteration of the vectorized loop. And this is the way that you can indicate that to OpenMP. And then you have private, last private. And these work exactly in the way that you would expect them to work from regular OpenMP. Couple of limitations. So safe length I've already described, and SIMD length too. Aligned, it's only asserting that the variable base address is aligned to whatever. So you're saying align A colon 64. That means you're aligned to 64 bytes. It doesn't mean that every access to the array is aligned. It just means that the base of the array is aligned, right? And the other three I've already described, so we can move on. A very simple example of something that the compiler wouldn't vectorize because it wouldn't see any way to do it would be this essentially if statement, right? So here we're saying there's a safe length of 32, so you could unroll these up to 32 times if you had a vector length that was that big, and everything is aligned to a 64-bit boundary. If you want to compile something that has OpenMP Cindy, you can use with the Intel compiler -q OpenMP, or you can just use -q OpenMP Cindy. And that would not recognize something like OpenMP Parallel, but it would recognize an OpenMP Cindy pragma. There's no harm in using both of them together either. Something that you cannot do without OpenMP Cindy, or at least not without jumping through quite a few hoops in terms of the way you write the code, is to make sure that you write functions that are vectorizable. Normally, the vector pass in the compiler will say, hey, I can't vectorize this loop because there's a function inside, and if I cannot inline this function, I cannot vectorize this loop. Now, what you can do with OpenMP Cindy is you can declare a function as a SIMD function. What the compiler is going to do is it's going to try to generate multiple versions of that function, such that if the function is in a loop and the loop is vectorized, it can use the right version of that function with the right vector length and still know that it's safe to execute. And that will depend very strongly on the information that you've provided in your declare and your OpenMP SIMD instructions, right? So here you can see how to declare those functions both in C and Fortran. It's pretty straightforward, just pragma OMP declare, SIMD, and then a number of clauses that by now should be more or less familiar to you. The one that is not obvious is in branch, not in branch. If you say in branch, OpenMP will assume that this particular function is always called in a branch statement. There's always a branch statement associated with it. Not in branch is the opposite, and if you don't say anything, the runtime will assume that in some cases this function will be called in a branching statement, and sometimes it will not. So if in doubt, just don't use that clause so that you have the most flexible generation. A quick example of how to use this, we just have essentially on the top we have an OpenMP pragma declare SIMD for a simple function, and then on the bottom we have a different function called vec2, where we use a pragma OpenMP SIMD on a for loop that contains this function, right? And there's other alternatives, right? If you are able to inline that function, then you don't need this because the compiler might be able to vectorize the whole thing. But this is a way to manage to vectorize a loop when you don't have the ability to inline or the compiler is not able to do it for some reason. That uniform statement that you see on the top of the declare SIMD function, that indicates that A, B, and off have constant value through the execution. And that's just the base address of A and B are not going to change through this execution, and the offset is not going to change through the execution. It just helps OpenMP generate the right code for that vectorized function. Now, if you want to use both parallelism and threads and SIMD, parallelism and SIMD together, this is not a problem. As with most OpenMP statements, you can combine them. You can do a pragma OpenMP parallel for SIMD, and that will generate a team of threads. It will vectorize the loop, and it would assign blocks of work to each thread that are compatible with the vectorization that has been generated, right? So that does a lot of work for you, as long as you're sure that you don't have any dependencies there, or that you've declared a safe length that is long enough, or short enough, sorry, to avoid dependencies. Now, SIMD on Theta is not particularly complicated. As much as possible, you should ensure that both safe len and SIMD len are compatible with AVX512 that you have on Night Landing. So a minimum of 8 for double precision and 16 for single precision. Something that is specific to the Intel compiler is the processor clause. You can use the processor clause to add a little bit of additional information to OpenMP on the specific hardware being used and the specific ISAs supported. So you can use this processor Mike AVX512 to target KNL. This would just be a clause that you append to whatever you're doing. And then still remember that not all vector operations are created equal. You might vectorize this loop, but if you have lots of memory overhead to set up the vector instructions, it's still not going to perform. So remember that none of these pragmas, none of these things are a silver bullet for any of the problems we normally have, right? You still need to go back after you inserted this and make sure that not only your results are correct, but it's actually doing what it's supposed to do. And there's been enough, I think, discussion on tools that allow you to detect that, both from the Intel side of the business and from others in the room. So you have the tools on Theta to do that. Don't neglect to do it, right? And now for the final part, I'm going to discuss Affinity a little bit. I'm going to concentrate on OpenMP Affinity. So if you're somebody that loves KMP Affinity, I'm going to give you a couple of hints to see how there's a very simple mapping from one to the other. If you only ever use app-run Affinity, well, maybe I convince you that you need to think about that a little bit more, even though I don't have any performance examples, but hopefully you can see the benefit of using and the simplicity of using some of this. OpenMP 4 introduced the concept of places and types of and policy bindings. So places that you can locate your threads during runtime, and how the threads are positioned inside those places, how free they are to jump around, and so on. And this is controlled with two environmental variables called OMP places and OMP proc bind. Now, if you have just pure OpenMP on Theta, you're running on a single node, my recommendation would be that you just tell app-run, I don't want you to set up any affinity for me. Do -cc none, and then you control yourself the affinity. You could use KNP HW subset and KNP affinity to define places and policies for binding. But since we're talking about OpenMP, let's go over these particular environmental variables and see how they work. So the first step is to define where your threads are allowed to run. And to do this, you can use your OMP places policy. There's 3 predefined policies, which are sockets, cores, and threads. So in places, you can do threads, cores, and sockets. And those are pretty obvious, right? If you set your places to the socket, any threads are going to be able to float around in the socket. So the OS might be able to move them around from one logical processor to another. If you just specify cores, then the binding is going to be made to cores, and you can only float around within a core but not move to a different core in the socket. And with threads, you're essentially binding to a logical processor. So in KNL, that would be thread 64 on the first core. You can also specify a list and define your own places if you don't like the defaults. And the way to do that is using this syntax. I'm going to give you an example in a minute so that it's more clear, because that syntax is a little bit annoying. But essentially, you have a lower location, which is where you start in terms of logical threads, where are you going to end and what your increment is. And then you can repeat that at a certain increment to generate essentially subsets that might skip certain cores or certain threads if you want to do that. Now, the second step is to set OMP proc bind, and what that says is, well, you told me that I have to bind to the core, but how? Am I allowed to float in the core? As in, what's my initial assignment? Am I going to be just on as close as possible to the master thread? I'm going to be as distributed as possible in the hardware. So these are the close, spread, and master policies. So when you specify close, threads are placed as close to one another as possible. If you're familiar with OpenMP Affinity Compact, this is essentially the same thing. It's a little bit dangerous if you don't pay attention to what you're doing, because you're likely to use only a fraction of the processor. If, say, you're using 64 threads and you say close, you will end up only in the first 16 cores because you have 64 logical threads, right? So you will be throwing away 3/4 of the performance by doing close. But there might be some cases in which you actually want to use close. A spread does the complete opposite. It spreads the threads through the system, but it is a little bit different from the OpenMP Affinity scatter. The scatter does round robin. The spread is a little bit more intelligent. It spreads through the system, but threads 0 and 1 are consecutive in the hardware. So they're as close as possible in the hardware while still using all of the hardware that is possible to use. Master is the most dangerous of all of them. It tries to place all threads right on top or as close as possible to master. So if you had a binding that was to places core and then you put everything close to master, you can imagine you can end up with 256 threads, all smashed in one core, and horrible things could happen. If you want to check that with every script that you submit, if you want to have a record of what you actually set in your bindings, you can use this OMP and display amp equals true, and part of that output will include the bindings that you set. So that's pretty useful to have a record of how your things run. Now let me give you some examples, because for me this is the best way to see how the binding actually happens. So the first example, I have 4 threads. Well, I'm going to have 4 threads for all the examples just to simplify, because otherwise I need to keep writing tiny numbers in the screen, and it's not really useful. And first, I'm going to declare OMP places equals 0, 4, and 2, which means I start at logical core 0, I end up at 4, and I skip every 2. What that's going to bind things to is to 0, 2, 4, and 6. Which sort of makes sense because, it makes sense because you start at 0, you have a length of 4, not an upper limit of 4. This is what always gets me. And then you skip every other. So this is fine, but I personally find defining OMP places as a custom thing, doesn't help me very much. The next example uses an OMP places equals threads, which means I'm going to bind this specifically to hardware threads, and I'm going to not be allowed to move around. And my proc bind is set to close. And in this case, if you look at the output from your binding statement, you will be on those threads, 0, 64, 128, 128 and 192. And those look like they're spread out, but those are actually the 4 threads on core number 0 on a KNL, right? Because the way the logical threads are numbered on KNL is it starts with thread 0, core 0, thread 1 in core 1, 2 in core 2, and so on and so forth, until it starts again with 64 in core 0. So what this is giving you is 4 threads. They're all bound to specific logical cores. They cannot move around, and they're bound inside, and they're closed, so they have all been assigned to the same core. In the next example, what I do is I use the same 4 threads. They're bound to a thread specifically, but the proc bind is spread. So they should be spread around, and that's what the report actually gives you. You will end up with threads bound to logical cores 0, 16, 32, and 48. And if you look at how cores are spread out in KNL, this is exactly dividing the KNL by 4, and you end up with core 0 with thread 0, core 16 with thread 16, 32, and 48. So this is exactly what I wanted to do. I want to have 4 threads spread out as much to use as much of the hardware as possible, and they're bound to one specific logical thread, right? Now, something that I find gives me typically the best performance, especially for codes that use 1 or 2 threads per core on KNL, is to set the last combination in the screen, which is a spread and core. This means that each OMP thread or task would be bound to a core. So it would be allowed to float on any of the logical processors assigned to that core, which means that my first thread, thread number 0, is allowed to bounce around in the first core that is comprised of those 4 logical IDs, 0, 64, 128, 192. The second one goes to a core that is essentially a quarter of the way into the KNL. There would be 16, and then 16 plus 64, that plus 64 again, that plus 64 again. So what this does is this spreads my 4 OpenMP threads so that I can use the hardware as much as possible. And still I have the OS has some flexibility. If the OS decides to put something on logical processor 1, for example, and I have a heavy thread running on number 1, it can be displaced to 0. But well, in this case, I don't have number 1, so it would have to be on 64, for example. My actual thread could shift to 0, and still it's using the same level to cache. It doesn't have to do any major rearrangements, so the amount of performance that I lose is minimal. If I bound that thread to the logical thread, and then the OS decides to put something there because I'm not using core specialization, for example, then I don't have an option. I need to time share, and I'm delaying all the execution in the rest of the processor, right? So I find these letting things float on the core pretty useful. Now, if you're doing hybrid execution, which you probably are if you run on Theta, you need to know how to set this up for a hybrid MPI plus OpenMP. And the way that you do that is that you set up areas of the processor where your ranks are going to run. And the way you do this is with the app run affinity settings. So you use a depth that is appropriate. You say how many threads you're using per core. And inside those regions that have been assigned to you, you use your OpenMP affinity settings. So the example I have here is going to use 4 MPI tasks, 16 threads per task, and a total of 8 nodes, which actually doesn't matter because every node is going to get the same affinity, right? So if I have 4 MPI tasks and 16 threads per task, I have 64 total processes running in the kernel. If you look at task 0, MPI task 0, could be rank 0. The first thread for rank 0 is going to land on the first core. The second thread for rank 0 is going to land on the second core, and so on and so forth, until I hit thread number 15, and that's going to be in core number 15, and then 15 plus 64, and so on. So those are the 4 threads that correspond to core number 16. MPI rank number 1 is going to start on core 16 and have a contiguous assignment, which each thread is still allowed to float on the whole core, right? So the way this has been set up is I'm going to use -cc depth with a -d of 64, and then I'm using -j4, so I'm using the 4 threads per core. And the only other thing I had to set up was my OMP places and OMP proc bind. Now, 2 more slides, and I'm done, and I can let you go on to the exercises or whatever you want to do next. A couple of things. Think about NUMA considerations when you're using OpenMP. Think about the way that you're initializing your threads. For many of you, this will be something you already know, and I don't need to remind you, but for others, it might be new. Linux has a first touch policy. If you allocate and initialize all your memory in a serial region, and then you move to a parallel region, you're going to have lots of remote accesses. On KNL, this is not that big of a problem because you have a single socket. It's probably not too terrible. But if you have dual socket systems, that could be reasonably bad. Also, the way that you use your MCD RAM, unless you're running on cache mode, you're going to have to tell the system how you want to run things. Because if you don't say anything, by default, you will be running out of DDR4, which is fine if you're latency bound. But if you're memory bandwidth bound, you want to make sure that you're using MCD RAM. And in that case, you can use any of those 2 commands using NUMA control -membind = 1 or prefer = 1. So finally, what I would recommend for you for setting up your affinity on Theta, and if you find something that performs better for this in general, not just for one application, I would appreciate if you tell me, because I did a few tests tonight, and in general, this was the most beneficial, is to set your places to cores. Even if you have more than 1 thread per core, I would still set my places to cores, my proc bind to spread, and then just make sure that I do my rank assignment using -cc depth, and then -d would be 256 divided by the number of MPI ranks per node. Now, if you're using lots of threads, particularly if you're using many threads per core, you might want to try this variable, OMP wait policy equals passive. That can sometimes help you with some of the synchronization overhead. So it might be worth checking if you see that you're having scalability problems with OpenMP. And that's all. Any questions? Yeah, the question is there a way to find how many tasks are running? You're referring to OMP tasks, OMP thread. Other than actually looking at all the process IDs that hang from your tree or printing out from your own code inside the region, I don't know of any environment that will actually report that, because that's a dynamic value through your execution, right? So I don't know of any obvious way to automate that. Questions? Thank you very much. I think